When a vehicle enters an emergency stop, the kinetic energy converted into heat at the brake rotor is massive. To manage that violent deceleration without losing traction, the hydraulic pressure modulating the brake calipers must be controlled with absolute precision. This cutaway of the Magnus kernel architecture shows a highly integrated mechatronic system, with the electronic control unit sitting directly atop the hydraulic control unit. Performance charts in the top right show strict constraints: 20 megapascal operation and sub-10 millisecond pressure modulation responses. Engineering a system to meet those aggressive targets creates a massive administrative bottleneck. Teams are forced to manually align a multi-level bill of materials with strict functional safety requirements across isolated mechanical, electrical, and thermal departments. Mapping out the risk analysis and test planning for these interacting components typically consumes up to 6 weeks of cross-functional meetings and spreadsheet updates. Manual tracking of how physical risks and constraints cascade between domains generates the primary delay in the hardware development cycle. The Magnus Genesis autonomous pipeline addresses this specific delay, condensing weeks of cross-functional alignment into a few hours of computational synthesis. This visual traceability matrix reveals Genesis's core solution: a relational database linking the physical bill of materials to failure modes and parameter diagrams. Tracing connections from requirement to risk nodes automatically predicts cascading failures before a single prototype is cut. This embeds design for reliability into the engineering architecture on day 0. Teams no longer have to wait for a physical prototype to fail on a test bench to discover a systemic design flaw. This is the system's hierarchical bill of materials. The synthesis process begins by mapping this strict architecture, logging every item from the L1 system level down to the L4 individual parts. With the physical parts logged, the pipeline maps the topological logic flows across functional domains. You can see the blue-bordered blocks and dashed sequence lines linking cross-domain requirements, like connecting thermal interface regulation directly to mechanical stiction mitigation. We can examine this using a specific component. In the center right of this exploded view is the thermal interface material, an alumina-filled silicone pad sandwiched between the ECU and the HCU chassis. Magnus defines these physical interfaces as explicit, trackable data objects, assigning them rigorous mathematical properties that quantify the interaction between parts. By forcing physical interfaces to function as rigorous mathematical objects, the software prevents boundary diagram gaps that cause late-cycle failures. Once static components are mapped, the system translates them into active physical operating windows using robust design principles. This generated P-diagram defines how the thermal interface material behaves under stress. Bottom control parameters are dictated by engineers. Top noise factors are uncontrollable external stresses. If noise overpowers controls, the system calculates error modes, like thermal runaway. All interacting parameters are calculated against an overarching target system reliability constraint of 99.7%. Mathematically quantifying these physical boundaries forces the architecture to generate its own predictive risk assessments autonomously. This drives the pipeline's most complex output, the relational design failure mode and effects analysis. The software constructs a 3-level effect chain to track how microscopic material variances cascade upward into catastrophic system failures. Tracing the interface, the model identifies a root cause, polymer chain scission. Moving up, this causes an L1 local effect, increased thermal resistance. This traps heat, forcing the L2 next assembly to exceed temperature limits, triggering an L3 system effect, total ABS shutdown. To rank the danger of these failures, the system uses a standard equation, multiplying the severity, occurrence, and detection ratings to calculate a risk priority number, or RPN. For the thermal interface silicone bleedout, the pipeline calculates an RPN of 216, automatically assigning it a high action priority. Compare that to the mechanical parts in the lower section, like the elastomeric decoupling mounts, which score an RPN of 140 for compression set deformation. This approach transforms the FMEA into a dynamic, calculated consequence of the system's topological physics. Before generating physical tests for these risks, the system mathematically verifies the physical validity of the architecture. It applies Buckingham pi dimensional similitude, resolving the length squared times stress over force balance to ensure physical consistency across all components. Only after that verification does it produce the final output of the pipeline, the design verification plan and report. These calculated risk profiles directly dictate exactly what needs to be physically proven on the mechanical test bench. Looking at the green nodes within the traceability matrix, the FMEA risk for silicone bleedout is directly linked to test ID T500. Zooming out reveals the operational implication. If an engineer pushes the hydraulic pressure limit past 20 megapascals, the architecture instantly reacts. That single parameter change automatically updates the bill of materials topology, recalculates the noise factors in the parameter diagrams, and outputs a revised list of required physical tests. Unbroken digital traceability condenses what used to be weeks of cross-functional engineering into hours. It removes the manual administration from systems design, accelerating the baseline velocity of hardware development.